hope and previous hopes, I think they're great.
I have a couple of copies which I'll pass around so you guys can flip through it, but what I want to talk to you today about, let me get this thing higher, is some fun stuff I've learned in the last year in the kitchen. And we've got a few things to pass out as well, so you get some treats and goodies to take home, and we're also going to do an experiment or two with audience participation. Can't say that today. So yeah, that's not working. Great. I'll be a minute while I figure out why it's not working. Hold on. We'll get there. It shows the display. It's just like not displaying. Yay! You have birthday karma magic. Okay, so I will get the slides up. In the meantime, I'm going to tell you what's in the box because I'm going to hand these out. These are little kits. I'll get to them in a minute, but what you want is one for every other person in the audience because there are actually 2 test strips in each of these kits, and I only have 50 bags, and there look like more than 50 people in here. So, again, pass out. There's no difference between the 2 different types. One's cooler looking. Oh, can you hand me one? Yay! Okay, cool. I'm going to move this too so I can actually see the screen. So, hi, I'm Jeff Potter, author of Cooking for Geeks. Books I will hand around later so you can see what it looks like. That's my friend Carl. I went to college with him. He's a really cool guy, and he actually is the first person who showed me this whole concept called sous vide cooking. I heard one awesome. Does anyone else here know what sous vide cooking is? Oh, I like you guys. Okay, so that's an egg that's been cooked sous vide. Basically, when you cook an egg this way, it gets this amazing texture where the egg yolk and the egg white have kind of the same texture. It's kind of plastic, it's kind of like mayonnaise. Tastes amazingly good. Here is a little video of me like cracking an egg that's been cooked this way, just so you can see how they kind of come out of the shell. The really cool thing about them from a cooking point of view is that you cook the egg, you crack it, and it just kind of drops out. You don't have to do this whole trying to scoop a soft-boiled egg out of the shell type thing. And it's magic. It just kind of works really, really well. And there's this question of, well, why is that? When it comes to an egg, there are different proteins in that egg, and the egg begins to cook at different temperatures. And there's this really, really narrow band where eggs are like perfectly cooked. Below that, they're raw and runny. Above that, they're overcooked. And that band's 144 to 158. When you drop an egg into boiling water, you can kind of imagine that egg getting warmer and warmer and warmer, and eventually, it overcooks. And if you take a hard-boiled egg and let it, sit in water, it's completely cooked. And you can actually overcook it. They're still good, but they're not this ideal, amazing egg. So the question is, how do you actually get that nice texture of an egg? When we do a soft-boiled egg, you drop it in, you pull it out after about 5-7 minutes, whatever it is, kind of trying to catch it on that blue curve as it runs up before it gets too hot. But what if there were a way to actually cook an egg where it couldn't overcook? Where you actually cook it in an environment that isn't above 158. And that's kind of the main principle of sous vide cooking. One uses a water bath, and there's a piece of electronic equipment called an immersion recirculator that basically keeps that water bath at a particular temperature. And this is something that's kind of pulled out of the chemistry world, where they need to do particular experiments or whatever at a controlled temperature. And in the 1970s, actually, this French dude figured out, hey, I can take this into the kitchen and do some interesting stuff with that, and repurposed chemistry equipment to actually working in the kitchen. And if you think about it, cooking's really nothing more than chemical and physical changes in food. So everything that works in a wet environment, from a wet lab point of view, works in the kitchen. So this is really probably the most successful and most popular thing. Sous vide cooking is being done in a lot of high-end restaurants, definitely here in New York per se. There's a bunch of plenty of others. I don't know where you guys are from, but most likely your hometown, there's at least a couple of restaurants that are using this technique for cooking. Let's see, a little video of eggs cooking. I mean, it just kind of shows you there's a little agitation in the water. It kind of mixes the water up so that you don't get this heat gradient. It works not just in eggs, but also works in steak. So this is kind of an exaggerated photograph of a normal piece of steak that's been cooked, just pan-searing it. You'll see there's this really nice, gradient of doneness, kind of this bullseye thing, where the middle's like rare and the outside's like kind of well done. Yeah? I heard one person going, yeah, am I making you hungry? Sorry. So the same thing for steak is true as with eggs. There's this really narrow range where meat's actually really, really good. 122 degrees, one protein in meat, myosin begins to denature and change texture. Around 150 degrees, there's another protein called actin that also denatures and changes texture. For really no particular reason other than just sheer dumb luck, we happen to prefer when myosin is denatured and cooked and actin's native, which ends up being, from a food science point of view, kind of in this 140 to 153 degree Fahrenheit temperature range. And if you're thinking, hey, that lines up with medium rare steak, you're absolutely right. Medium rare steak is pretty much in that ideal band. Let's see. So there's a little gradient of doneness chart, kind of shows you roughly, under normal circumstances when you cook things, heat goes in from the outside in, and the outside eventually gets hotter than the ideal temperature, because in most cooking environments, the environment's actually hotter than your target temperature. But when you go to do something sous vide, like the piece on the right, what you get is just this one entire block of meat that's medium rare, or whatever you set the temperature to. So the whole thing is like this amazing texture, amazing flavor, really good texture. It's great. Now, of course, you notice the piece on the left side has this nice brown crust on the outside, and the piece on the right kind of got this kind of gray matted look that's not so good looking. Yeah? So what we do in cooking this stuff is after actually sous vide cooking it, you take it out and you drop it into a pan and you sear it really quickly just to get the outside nice and browned up. Yeah. So these are my friends, Ed and Jamie, and what they're doing is they're taking a piece of meat, putting it into a vacuum bag and sealing it. And the reason this is done for sous vide stuff is it prevents the water from coming into chemical contact with that food. The water's only about heat transfer. It's just about getting energy into the system. It's not about actually doing anything with the meat. So by sealing it in a plastic bag, what you get is something where any flavors aren't getting washed away essentially. It's also a lot easier to work with, frankly. I mean, a piece of steak floating in water is kind of vaguely gross. So that's what it looks like uncooked. That's what it looks like cooked. And that's just a little photo of me, pan-searing a piece of meat. You can do other things. Fish works really well. Lobster works really well. You can actually seal other stuff in that bag. So for the lobster, I actually did it in this butter-water mixture. So, the lobster itself, imagine that shell trying to get it vacuum sealed. Like, that just would be impossible. But if you put other stuff into the mixture, you can do marinades or whatever else. So this whole thing is sous vide stuff. It started out with industrial controllers, which are really pricey. They're kind of in the $1,000 territory, which is just insane for somebody at home. There's a company called Sous Vide that came out with this unit called the Sous Vide Supreme this last year. It's about $400, but we can still do. Say what? Supreme? S-O-U-S-V-I-D-E. 2 words. You own one? Who said that? You're the same guy that said yeah earlier. I do too. I mean, these things are great. I mean, you have no idea how amazing it is. I mean, Trader Joe's sells fish vacuum packed in bags with marinade in it. It's like it can't get any easier. You take the bag, you drop it in the water, and you go to the gym or go for a walk. I mean, thinking about that curve with the ideal temperature, the water's not hotter than that, so it can't overcook. So you can just let it sit in there for an extra half hour. So from a timing point of view, as long as it's been in there long enough to actually cook, it's good. So it's yeah, this stuff's great. I mean, it's so easy. It's go, trust me, try it. You can make your own rig. You can go buy a JLove controller and drop a thermocouple into a crock pot, just interpose on the power. Make sure you get a dumb crock pot, one that you can switch on, that doesn't then decide to turn off and not turn back on if you cut the power. You know what I mean? So you can do that for $70 or $80, which is kind of in the realm of, hey, I actually am willing to go try and do that. And it's definitely worth it. So that's just a really quick primer kind of on sous vide stuff. More generally though, why do we cook? What's the actual purpose of cooking? I mean, it's kind of nutritional stuff. There's, some amount of it tastes better from a textural point of view. But the real question is, why learn to cook? why do we actually want to go into the kitchen when, like, say here in New York, it's practically cheaper to go down the street and buy something from like Picante or whatever, and it's gonna be really good and cost you like $7. So, think about the reasons why you cook. I mean, why do you guys like to cook or want to learn to cook? Because you have a girlfriend. Okay? What else? It's fun. Meditative. Dietary, you get to choose. We don't live in New York. Where do you live? Toledo, Ohio. You so want sous vide, man. Trust me. You get to buy knives. Well, you can do that without cooking. You just, have knives. So there's this kind of nice little simple model about cooking. You can think about it as inputs. These are your ingredients, things you actually go and buy at the store. Cooking is the actual bit of, I'm going to change this thing. I'm going to slice it, do some chemical, physical modifications, blah, blah, blah. Sensations are like how it smells, how it tastes, kind of, what the objective, everyone would agree that thing is pink, for example. And there's kind of perceptions. And these will be things like your emotional reaction to it. Hey, this reminds me of my childhood, or my grandmother's brownies tasted like this. So there's this researcher down at Cornell, a guy named Brian Wansink, who did this study of about 1,000 cooks, asked them a bunch of questions, did this K-means cluster analysis, and came up with this really nice little typology of like 5 types of cooks. And it actually turns out to be really kind of fascinatingly useful, because when I'm talking to somebody about why they cook, I can pretty quickly go, oh, you're like this type of person. And he really kindly developed this 5-question quiz, which I just so happen to have. So the way this works, I'm going to run through each of the 5 questions. Just keep track of which letter you're answering. So if there's 5 questions. So if you answered, say, A on all 5, then you're type A. It's like not that difficult. So you don't even have to write it down, but you can if you want. So you guys ready? Okay. When I cook a meal, I typically ... Are we good? Should I go on? Anyone gonna say no? Okay, that was a dumb question. Some of my favorite ingredients are... If none of the above, then just don't count that letter. So when he did the research, he only actually fit like 80% of the population. And like some people just are like this hybrid blend between different types. So I mean, like, don't take this as like, oh my God, I am this type. I have never like, it's not exact. Next one, ready? Okay. In my free time, I like to... Okay, well, for this crowd, there's probably like an F, which is like... Work with me here, people. Wait, what? What? Yeah, okay. Just answer D. My favorite things to cook are... No soldering iron references here, please. You don't cook junk food. Junk food's like extruded. It's like, doesn't... Okay, are we ready? Other people describe me as... I should go through the slides and edit them and add type F at the end, which is like next hope attendee. Okay, so everyone kind of had a chance to get their letters down, figure out what you are, drum roll. Okay, so here are the types. So giving, this is somebody who shows nurturing and affection through like baking and taking it to their work or whatever. Healthy, this is somebody who brown rice, veggies, fish, steamed stuff, and could care less about how it looks or how it tastes. Methodical, this is somebody who can make it look just like the picture, but their kitchen will look like a nuclear bomb's gone off, but it'll look just like the picture. Innovative, this is somebody who reads a couple of recipes, goes into the kitchen, goes, yeah, I'm gonna try this instead, and either it comes out or it doesn't, but they're happy with it, or they're not and they don't care. And then the last type's competitive, intense perfectionists. People who like to grill generally fall into that category. Not that there's anything wrong with grilling, I like to grill too. So just a show of hands, who is A? B? C? D? E? So the interesting thing is the general population is like 20% for each of these. So here we have scientific proof that you guys are not like the rest of the people out there. So going back to that little chart earlier, you can kind of roughly map that type onto what your motivations are. So for me, like, you know, I'm kind of a blend between B, health conscious, and D as well. But definitely, you know, that cooking bit and thinking about the inputs for me is really important. There's also, you know, the other reasons. And understanding that when you go into the kitchen is really important, because if you're like, say, a health-driven person and, you know, broccoli and brown rice does it for you, and like you're dating somebody who's like, you know, this person who likes to bake baked goods all the time, like you're by definition almost going to set up this kind of aggressor type thing between the two of you. So understanding that it's not, you know, it's not her, she's not trying to get me fat or whatever it is, you know, it's just people have different types. So besides, like, you know, psychology, there's also physiological differences in the way we taste and how we are. That's where this thing comes in. Some people will taste these things, or I should say, some people will like these things more than others for actually an interesting physiological reason called super tasting. Who here has heard of this before? Oh, cool, you guys are well informed. Who hasn't heard of it? That's a better question. Okay, I like you people. Okay, so if you've done this before, skip actually doing it. And how far back did we get with these? Who does not have, or sitting next to somebody who has one of these? Ooh, sorry, back half of the room. Consolation prize for you later. So what we're going to do is go ahead and open this up. I'm going to toss this one back so somebody can catch it back there. Maybe? So yeah, pass that back. So there's two little strips of paper in there. Hand the person sitting next to you one of those. Don't put it in your mouth. Don't do anything with it yet. I swear it's not LSD. Yeah, it's great. Like, I'm giving out little strips of paper that are like coated with chemicals, and I'm giving out white powder. Like, I'm surprised I haven't been arrested yet. Okay, so the deal with this is it's basically a genetic test. I should give you two warnings. One, some of you won't like this. So like if you don't want a bad experience potentially, and there's a little candy in there. You'll know if you need that. The second warning is technically it's a carcinogen, so it's a really, really minor dosage. It's not going to do anything. So is the flight to get here, she says. You flew? Okay, so go ahead and stick that in your mouth. Little paper. Don't swallow it, just on the front of your tongue. Who said that? The candy's for you. She's like, this tastes like shit. Icky, horrible? Okay, so the people who are saying icky and horrible are like this, my person on the left here. Some of you kind of maybe tasted something. Like you can taste it, but like you don't get what it is. Like people are complaining. What? Evil aftertaste. Aspirin. Sour, bitter. Bitter. Okay, and then some of you are like the person on the right, John, who just like, you know, tastes like wet paper, right? Okay, so the deal with this is that some of us actually taste certain set of compounds. Really bitter. Others of us can kind of vaguely taste it, and some of us don't taste it at all. This is called super tasting. If you're looking at the percentages here, it is genetic. It's two genes. If you've got both dominant, then you are a super taster. If you've got one or the other, would gum affect this? Splanthulin, it might, but I don't think so. Why, you didn't taste anything? Yeah, you're a non-taster. Sorry. Now, a lot of people are like, oh, well, I had food in my mouth. I should do it again. It's like, no. You know, you'll know if you taste it. So then, yeah, it's a genetic thing. You know, if you've got both dominant alleles, you're a super taster. If you've got one or the other, then you're a medium. And if you don't have either, then you're a non-taster. It is differ based on gender. So females are actually a little more than 3 times likely to be a super taster. And it also differs based on ethnicity. So Asians are actually more likely than Caucasians to be super tasters. So on that piece of paper was this chemical called phenolphthalecaramide. Say that 6 times fast. It doesn't actually exist in nature, but it's similar enough to compounds that do exist. Oh, different slide, oops. Yeah, so tasting. It's just one of many thousands of compounds that we're able to taste. Like, it was discovered completely by accident in the 1930s by this DuPont chemist who like spilled some on his counter and he didn't notice. And like one of his lab mates was like, what's this bitter taste? And like all good researchers in the 1930s, he started testing on his family and friends, you know, before OSHA. Like I think researchers today are jealous of this guy because he could just like say, here, try this. So there are other compounds that are probably more significant than phenolphthalecaramide. But it's one that we happen to know about. I mean, there's something with cilantro. We know cilantro is genetic, but we don't actually know yet specifically what it is. But about 11% of people, it tastes like ivory soap. Say what? It's really disgusting, says the guy here. I happen to like it, so it's a genetic. I mean, this goes to the point of like, if I was cooking for you, like I'd have to know that there's a difference in physiologically that you don't like it, and keep that in mind, even though I love it. So that kind of goes to the point. When it comes to phenylphthalecarb, it doesn't exist naturally, but it's similar enough to compounds that do exist that people who are super tasters are less likely to smoke. They're more likely to add sugar or milk to coffee or tea to kind of cancel out that bitter flavor. They're less likely to eat green vegetables, and there's some thought that they're actually more likely to have certain forms of cancer because the glucosinolates, which I can never say, actually supposedly help prevent certain forms of cancer. Sugar tastes up to twice as sweet. There's other differences for super tasters as well. Things like capsaicin, what makes hot peppers hot, carbonation, soda, things like that, tend to be more irritating, quite literally from a cellular level, to people who are super tasters. My poor friend Shimon, immortalized in this great photograph. If you don't have one of these test strips and you really want to try this, you can put blue food dye on your tongue because the papillae, the little taste buds in your tongue, don't actually stain blue, and you can count the number of dots like in a 3-hole punch area. It's kind of a rough way of doing it as a proxy, so if you're like watching this like on a video, you can try doing this. It kind of works, but it's kind of hard to do. But it's doable. Just put it out there kind of as a note. When it comes to bitter, when it comes to bitter in cooking, we use salt to kind of cancel out bitterness. So things like quinine, this is what's in soda or tonic, sorry. If you put salt into that, it'll actually become less bitter. So it actually literally cancels it out. So if you're somebody who can taste certain bitter compounds, you taste them more, you're gonna use more salt. So if you're like, say, cooking some Brussels sprouts and you throw salt on top of it to kind of cancel out that bitterness, and you taste Brussels sprouts as more bitter than somebody else, to them, it's gonna taste too salty. So keep that in mind too when you're cooking for somebody. It's not a bad thing to necessarily leave like the salt out on the table for people to kind of adjust the seasoning to their own personal preference, because there really are like literally genetic differences. 5 tips to make things taste great. Yeah, taste, adjust, repeat. So what I mean by that is taste something, don't just blindly follow the recipe. Taste it as you go and kind of think, hey, what could this use more of, or what's kind of missing. Balance of salt and acid. So we tend to think about seasoning as being just salt, but there's actually 5 or so primary tastes that you can kind of adjust. So a little bit of vinegar, a little bit of lemon juice in something can often kind of add the dimension that's missing in a dish. Primary taste, salt and sweet. I did this demo earlier this week with feta cheese and watermelon. It's like you can just make a salad of feta cheese and watermelon, a little bit of red onion. It's really, really good. And most people are like, I would never think these things would go well together, but they go amazingly well. A lot of that kind of comes down to, well, these primary tastes, certain things go well together as primary combinations. And in fact, kind of any double of primary taste ends up having something that matches, with the exception of, I think it's like bitter and, I'd have to look it up. There's like one I couldn't find an example for. But it's kind of a good thing to keep in mind. Like, if you've got something that's very kind of one-dimensional, think about it from a taste point of view, not necessarily from a smell or odor point of view, and think about what are the other primary tastes that might be good to add in there. Thermometer over a timer. Going back to kind of my sous vide bit a little while ago, when you're looking at, say, a piece of steak and you're cooking it, what matters is the chemical reactions in that steak, the proteins actually denaturing, and those things happen at certain temperatures. And yeah, to be clear, it's a time at temperature reaction, but it's not like your chicken. Let's say you've got a 6-pound chicken you put in the oven, and your timer says 45 minutes. It's not like 45 minutes matters. What matters is the internal temperature of that chicken for those chemical reactions. So when I say thermometer over a timer, timer's a good reminder of, hey, time to go check it. But really, using a thermometer is a great thing, especially in cooking meats. And finally, don't poke at things that are searing. If you've got some stuff in a pan, and you're trying to sear the outside of that steak, it's conforming to that pan really well when you drop it in initially because, well, the outside of it's raw and conforms well. And if you disturb it, it's not going to have as good surface contact, so it won't cook as well. So like you're, sauteing veggies or cooking meat or searing anything, just let it sit and rest in the pan. Like one of the most common mistakes I've seen with people cooking is like they just constantly feel like they have to do something and stir it. So don't. Okay, I'll take a break here for a minute, and I'm sure there are probably some questions because I know I've had a few people look at me. Go for it. 2 questions.
So on the sous vide, let's say you set it to 143 degrees.
Sous vide at 143, okay.
Can you overcook the meat after it's been in there 25 hours?
Can you overcook meat after 24 hours at 143? I'm going to say no with a little asterisk. No, you can't overcook it, and in fact, you can make really good brisket that way. So things like collagen actually take a long time to hydrolyze and denature and break down. This is why like duck confit, like you have to cook it for like at least 4 to 6 hours before anything happens, because it's not literally just a temperature reaction, it's a time at temperature reaction. Something will change. And the little asterisk there is that there are some types of meats, and especially fish, where there are certain enzymes that are present. Those enzymes will begin to react and break down the flesh. So if you do fish, you'd actually do fish at a lower temperature because fish myosin begins to denature around 100. He asks if there's a comprehensive chart of this in the book. He says, flipping through the book, here, just look at this. Next question. If you want a really good reference for sous vide stuff, Douglas Baldwin, just Google sous vide primer, S-O-U-S space V-I-D-E primer. I interviewed him in the book, so there's an interview with him in there. You can email me. My email address will be up on the last slide. I'm happy to answer questions via email. But he's got this great, kind of chart of thickness of meat, time, and temperature. And we'll get a little bit into the food safety stuff because there's a little bit of stuff you need to know that's, don't just go do it. But 143, given sufficient hold time, you're totally fine. Salt cancels out bitter, he asks. Is it masking or canceling it out? I'm not a physiologist. That's a really good question. I don't think it's actually, I could take an educated guess. I mean, you have different receptors on your tongue for salt, literally like ion gap receptors. It's not, no, I don't think they're actually bonding and like forming a different thing. I think it's still there, but that's just an educated guess. Other questions? I'm gonna go with the guy in the red, black, whatever color it is. Sous vide question was, is sous vide cooking useful for veggies? I personally don't find it so, normally. There are people that, if you look at Under Pressure by Thomas Keller, he's certainly got stuff in there for like asparagus and stuff. Veggies undergo this really interesting phenomenon around 55 degrees Celsius, 60 degrees Celsius, like 130, 140. They actually get firmer. It's like really counterintuitive, but if you like take a carrot and you cook it at 60 C, the cell walls actually, there's crosslinks that occur in calcium ions in the cell walls that actually fortifies it stronger. So if you actually look at carrots in like commercial soups, canned soups. Think about canned soups that have all these veggies in them. And, like you take it home, you heat it up, and like the carrots are still firm. Like how do they do this? Because it's not like they're carrots. They're growing in the ground. And if we do that ourselves at home normally, try putting some carrots into stew. Like half hour later, they're mushy. And what they're doing is they're holding them at 60 C for like half an hour, which firms up the cell walls. So I mean, there are some like industrial applications where it's kind of useful and kind of cool, but I don't know if I feel like making canned soup and storing it. I usually eat it. So I mean, the only other thing I really do with sous vide and veggies is like, I'll sometimes take bok choy and like cut it in half and like drop it in the water along with maybe some steak tips I'm cooking. I mean, it's water. It's just you don't vacuum seal at that point. You're just basically kind of power cooking it, and then I'll drop it into a pan and steam it or sear it really quickly. And there, it's just it comes to temperature faster. It's basically preheated. But from an actual cooking it point of view, I personally haven't really found anything that's like, oh my God, this is easy and amazing and tastes really good. I mean, if you're in the commercial restaurant world, yeah, absolutely, there are things they do, but they're kind of beyond what I found worth it. Green shirt. Okay, I'm sorry, can you speak up? You would normally cook them separately. I mean, you wouldn't want the veggies in that bag with the meat. It just doesn't really, I can't really think of any applications where you'd want to do that. I mean, maybe you would for like, I don't know, sage on the outside of something where you want the flavor present in the meat. But if you actually think about marinades and meat, marinade doesn't actually get very far into the meat. It only gets to like in the first millimeter. So in terms of like getting the flavor into the meat, unless you're brining it for a long period of time, like the flavors aren't going to transfer from the veggies to the meat. And in terms of like the veggies themselves picking up flavors from the meat, you're going to pan sear the meat probably afterwards, so toss your veggies in that pan if you want to do that. But in most cases, I haven't really, I haven't noticed it being different, I'll put it that way. So you're kind of asking what about the juices from the meat and what to do with them? Well, when you take that bag out of the sous vide bath, you snip it open, pull the meat out, there will be liquid left over. You can take and reduce that down, make a pan sauce or whatever you want with it. And so if you want to mix your veggies in that, that would certainly work. I'm not sure if I answered your question. Feel free to come grab me afterward. Blue shirt.
Yeah, I'm kind of curious about your decision to focus on a meat-based diet in the context of a hacker conference that's really concerned with social change.
Sure.
Given there is negative ramifications of carnivore diets, both socially and environmentally.
So you're kind of asking about, say what? I look at it kind of from the science point of view, and to be clear, I'm only talking about like 10 pages out of 400 so far. So the book itself really has a lot of different stuff, including kind of discussion of, hey, environmental impact of, say, beef versus chicken versus fish versus veggies. I understand where you're coming from, and I kind of share a lot of the same concerns, absolutely. Sure. Well, I'll get on to some more other topics that are less meat-based and a little more fun from that point of view. But thanks for the question. Black shirt? Cooking at sufficiently low, you're asking if the bacteria and what the bacterial concerns are. See that 131? We'll get there. Actually, how much time, where are we at? Yeah, we're halfway through. Okay. I'm going to go on to the next section and hold your questions. So 5 key temperatures in cooking. When I first started the project, I don't think I would have thought that this would have been one of the things that would have come out of it. But to me, I look at these 5 temperatures and I go, wow, these are really important temperatures. How come I never hear them talked about this way? So 122, sorry to go back to the meat bit for a little while, but bear with me, is when myosin begins to denature in meat. This is mammalian meat. For fish, it's around 104 to 106 degrees. 131. This is when the highest reported survival temperature of bacteria in the literature. So this is for a particular pathogen called B. cereus. I don't know who names these things, but that's the name of it. So the thing to remember about bacteria is it's not like they instantly die at 132. The food industry kind of has this danger zone rule that says you're not supposed to hold food between 40 Fahrenheit and 140 Fahrenheit for more than 2 or 4 hours, depends upon what state you're in. But the assumption there is that bacteria basically can multiply within that range, and outside that range, you're basically safe. But the reality of it is it's not like the bacteria are reproducing like full on at exactly 40 degrees, and at 39 they're doing absolutely nothing. It's much more kind of this curve, and it depends upon the particular bacteria how quickly they multiply. What food scientists and food safety experts are worried about is the quantity of bacteria and pathogens in a particular dish, whatever it is. And it also depends upon the strain of bacteria or parasite. But with bacteria, sometimes as few as like 5 is enough to actually cause an infection in you. In other cases, it takes like 100,000. So really, it's not just like are they present or are they not. It's not a binary. It's a question of how much exposure is there and what the probability is. So from a food safety point of view, the numbers that they give publicly are really all about this probabilities game of trying to make sure that from a probability point of view, you're safe. Because really at the end of the day, it sucks to have foodborne illness. And just to give you some numbers on foodborne illness, CDC estimates about 75 million Americans a year come down with something from foodborne illness. So most likely, you personally will have 2 or so foodborne illness incidences in any given decade. It's fine if you're a healthy young adult male like me, but if you're pregnant or really young or really old or immunocompromised, it can lead to much more serious complications. So when it comes to the bacteria and actually holding stuff at temperature, this is a curve for time at temperature. This is from the FSIS, which is a group under the USDA, for how long you need to hold. In this case, this particular one's for lean chicken breast, poultry. You have to hold that chicken breast at 136 degrees Fahrenheit for over an hour, almost an hour and a half, to actually sufficiently kill any salmonella that might be present. And the reason for that is that they don't die instantly. And kind of the analogy I like to give is imagine being in a desert. You know, it's 120 degrees. Actually, imagine like 100 of you are in a desert. It's not like at 3 hours and 59 minutes, you know, everyone's going to be alive, and at 4 hours, you're all going to suddenly die. It's going to be kind of some fall off. And so they're looking at sufficient log reduction of bacteria present in the particular meat. And it just depends upon the temperature and how long you hold it. So the last meat-based temperature here is 150. This is when actin begins to denature, as I mentioned earlier. It's kind of a nice little quick chart of, hey, there's this really narrow good range where stuff's really, really good. And you know, below that, you've got food safety or undercooked issues. And above that, texturally, it's overcooked. Last two, Maillard reaction. This is a really well-known one. This is the Brownian reaction in proteins with simple sugars. So things like bread, when you actually look at bread in an oven, you know, it starts to turn brown. The surface of that bread is like 310 degrees. And this is like one of the best moments for me in writing the book was I have an IR thermometer. It's basically looks at surface temperature of things. It's like best geek toy ever, like go and get one. And I pointed at a loaf of bread I was baking, like it registered 310 degrees. And I was like, yes, science lines up with reality again. So I mean, this is the same thing on meat. Different types of cooking methods will get you into that temperature range. So if you think about Brussels sprouts, you know, boiling them, like they can't get up to 310 degrees, like they're in water. So they'll never get that Brownian reaction. They'll always have this mild flavor. Whereas if you cook them with a method that can get that hot, then you're able to actually get those reactions and get the associated flavors. And the last one, 356, caramelization. It's basically sugars breaking down, and when they break down, they then like form hundreds of new compounds, and basically we like those flavors for some bizarre reason. One of the cool things is that you can actually see this reaction occur. So I baked a batch of sugar cookies at 4 different temperatures, and at 350 and below, they're kind of lighter blonde colored, and at 375, 400, you know, they get this darker color. It's not like a particular point where that caramelization really, you know, suddenly turns brown, but it's kind of this ramp from 356 up to 380, where sugar like gets darker and darker and darker, and you know, more complex and more bitter flavored. But sugar itself actually melts exactly at 367, which is this really cool trick because you can actually calibrate your oven using it. So if you throw a little sugar in a glass bowl and put in your oven at 350, like it might begin to caramelize and turn like slightly brown, but it should still be a powder. And at 375, it should melt and like just look like glass, and like be able to see through it. So cool little trick. You can also just throw sugar into a pan and melt it. There's nothing else in there but sugar. And when it comes to like making caramel sauce, like you know, the standard way is take sugar, add some water, you know, add some other stuff, you know, carefully boil all this other stuff. You can just throw sugar into a pan and melt it. Add a little cream. You won't be able to get like a light caramel sauce, but you'll be able to get a caramel sauce that's kind of a medium brown. And it's actually really fast and easy to do. So quick summary of temperatures. Peek at my next slide. Yeah, okay, we'll get there. I'll stop again here for a minute and take any questions.
So if caramelization is happening in Greece, whatever, why can you make toffee out of condensed milk just by boiling it, which can't be above 210 or so?
Toffee. Making toffee from condensed milk. Well, I'll need to check this, but sugar by itself will melt at 367, but when you dissolve it into something, you know, it's no longer a simple structure. That you're looking at something that's a little bit more different. The other thing is milk's mostly lactose, and I think lactose like actually begins to caramelize around like 230. Like fructose and lactose and a few other sugars, like they're not all in this like higher temperature range. No, that's sucrose. Yeah, common table sugar. Red shirt.
What about the temperatures at which important vegetable proteins are like particularly cellulose? And
Temperatures of veggie proteins. Well, not proteins, but yeah. Things like cellulose, well, I'm going to give you a hand-wavy answer, 140 degrees. Veggies are a lot more complicated than meat, which is why, from a food science point of view, it's really easy to talk about meat, and it's really hard to talk about vegetables. So I actually interviewed Hervé Thies for the book, and I was talking with him about this, and his lab's currently studying like vegetables, like a lot of stuff in vegetables, because frankly, there's not a lot of research done in that. In part because, well, who benefits from the research and who funds it? It's just really hard to get funding for some kinds of research where it's like, it's not applicable in industry kind of to some degree. So yeah, there's a lot of things we don't know about food. That really surprised me actually. It was like how little we know about food science yet, how much, you know, how important it is to us from a cultural point of view and from an industrial point of view and from a, Earth-life balance point of view. Yet at the same time, it's really complicated. So stuff like the chloroplasts, I think it is, in veggies, like you'll start to see reactions around 140 degrees. Chlorophyll, sorry. Stuff like cellulose and lignans and like cellulose is basically fiber. I don't think it begins to break down until like 300 something degrees Celsius. I mean, like, it's not going to break down in your kitchen. Or I should say, by the time it breaks down, you don't want to eat it. I mean, there are industrial ways of like grinding it and getting cellulose powders, but like, you're not going to want them. Go ahead. Changes in taste over time. Is that kind of what you're asking? Super tasting does not change over time. You either are or not. That's the genetic thing. There is a slow loss of sensitivity of taste, starting kind of in your late 40s, early 50s, and it's kind of gradual. Kids with bitterness, yeah. There's an aversion to bitterness from a physiological point of view, just because most poisonous things taste bitter. Like, it's kind of like a survival thing, I guess. But it ends up being that we can kind of learn to like bitter things. It's something that we with exposure learn to like. And there was one other, hot things. Hot things are really interesting, actually. There's this neurotransmitter called substance P. P stands for pain, go figure. Basically, it gets depleted. So if you eat spicy food, like this neurotransmitter that helps your body recognize, hey, there's something hot here, like it slowly depletes. And like it takes a couple of weeks, but after a couple of weeks, you can actually kind of deplete your levels down. And then it takes a couple more weeks for your body to replenish it if you stop eating spicy food. So this is where there's these really great stories of Indian students back in like the 80s coming to the United States, studying college, eating dorm food, going home, eating their mom's cooking, and going, this is too hot, I can't eat it. And their mom's going, what has America done to you? Nothing, other than they didn't serve you enough hot foods. Your substance P levels didn't replenished. So yeah, you can actually build up a tolerance to like specifically capsaicin and hot things. So I mean, yeah, there's that as well, which is actually really cool. Go ahead. Back to meat. Dum 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 dum. Umami and savoriness. Yes. Well, it's basically glutamate. So it's one of the 5 primary tastes that we know we have receptors for in our tongue. It doesn't break down with heat. So there are certain ingredients that have a lot of glutamate in them naturally. Things that go on pizza just happen to have a lot of glutamate. Tomatoes, Parmesan cheese, mushrooms. There's a reason why I think pizzas are so well liked. But yeah, I mean, MSG has kind of gotten a bad rap in this country, but like if you want more glutamate, like a small amount of it, I mean, it's gonna hit those receptors. But does that answer your question? Okay. White shirt.
Just to be clear on the facts, so like if I were to bake chicken, I might put it in a 350. When it's in the oven, does it only get up to 150?
Hopefully it gets to 150. Yeah, no, I mean, if you put chicken into your oven at 350 and your chicken actually got to be 350 degrees, you'd have a piece of charcoal. There'd be no moisture left. It'd be completely dry, and like, it would be the most overcooked chicken in the world. There's actually this really fascinating patent case that happened about a decade ago. These 2 different patents were written about like baking. I think it was like baking bread, and like one patent, like literally the process was baking bread at 350 degrees. Another one was baking bread to 350 degrees. And they were like suing each other in court, and they were actually found to not be infringing each other because literally one said you bake the bread to 350 degrees, which means a piece of bread baked to 350 degrees where it's like got no moisture left. But yeah, no, when you're cooking chicken, you want the internal temperature. Oh geez, this is gonna be recorded, isn't it? Maybe I should be careful about what I say. You want your internal temperature of your chicken to be 165 degrees, in quote marks. The reason for that is they assume that, well, as one food scientist put it for me, the numbers are for dumbasses. I'm quoting somebody. And she justified it and said that with those temperatures, they assumed that your thermometer was like a dial thermometer that's miscalibrated by maybe 5 or 10 degrees. So now we're talking about 155 degrees. And they also assumed that you misprobed the coldest part of the meat. So you weren't actually getting the cold part, maybe near the bone, but like just didn't quite hit the coldest part. So another 5 degrees. So it kind of gets you down to 150 degrees. The other thing is that number is an instant kill temperature. So that what that means is if you see chicken at 165 degrees, any bacteria that's present will be dead on that log curve thing, because like the die-off is so fast. But you can cook it, like if you actually, I mean, if you look at the industrial food processing guidelines, you can cook chicken at 140 degrees, as long as you hold it for sufficient time. And actually, it's really good. Because, I mean, saying medium rare chicken sounds really gross, but if you eat chicken, you've had medium rare chicken by fact. If you go to like ABP or, you know, McDonald's or any of these places where, you know, you get like a chicken salad and the chicken's kind of moist and like not dry, like they're cooking it at a lower temperature because texturally and from a moisture point of view, it tastes better, but you have to hold it for sufficient time. So like the guidelines they give consumers are, you know, they err on the side of food safety, which is absolutely the right thing for them to do. Because when it comes to, you know, would you rather have it taste good or would you rather have it be safe? It's kind of like a, well, who wouldn't want it to be safe? There's a really interesting little footnote to that, which has to do with ground meat. With things like chicken, they're generally, the temperatures are for the entire chicken, because salmonella can actually permeate through the meat. It's unusual. They're supposed to pull the chickens that are actually that sick aside, but it's potentially possible. With things like steak, though, where it's whole muscle intact, where it hasn't been cooked, hasn't been cut or jacquarded, it's only the surface that they really care about. As long as you pan-sear a piece of steak, the inside can be, you know, uncooked, completely raw. And from a food safety point of view, it's technically fine, which is why you can order things like your steak, you know, rare, but you can't order your chicken rare. But when it comes to, say, hamburger, where it's something ground up, the whole thing is outside. There is no inside. So ordering a hamburger, like, I kind of secretly want to go to like a food scientist convention and ask them this question, like, how do you like your hamburgers cooked? Because like technically none of them should answer anything other than well done. Because, you know, unless you actually hold it in a sous vide bath at 140 degrees for a sufficient time for bacterial kill-off, which you could actually probably make a really good burger that way if you're willing to go through the pain and the amount of work and make it safe. But yeah, just to answer your question, it's probably a really long answer, sorry. Okay, I'm gonna go for one more question, I'll go on. Black shirt in the back. Sushi, you mean from a bacterial point of view? Okay, so yeah, well, I mean, from a bacterial point of view, we can certainly talk about sushi. Things like tuna are actually excluded by the FDA from needing to be cooked. That has to do with, for tuna, there's no really bacterial pathogens that actually, like salmonella just doesn't exist in the deep waters of the ocean. Like, it's not like tuna get infected with that. And from a parasitic point of view, the same thing's true as well. Things like salmon actually can come down with parasites that can be an issue. It's pretty rare. But in that case, you can kill parasites by freezing them. So if you're really concerned about food safety and stuff like fish, you freeze it. There are certain time temperature hold guidelines that the government publishes. For fish, it's, I think, -20 F for 7 days, or like insanely cold for 1 day. But yeah, tuna is actually excluded, so tuna's fine. When I go to a restaurant, I generally like, you know, to order my tuna sashimi, not my salmon sashimi after doing this book. Does that answer your question? Okay, I'm gonna go on for a little more. Oh man, I have to go really fast because I have like 13 minutes left. Should I go really fast and like blast through this, or should I just like cut the last bit of it out? Blast? Okay, unusual temperatures. That's my oven, 845 degrees. If you clip the lock off of it, you can put it on clean cycle, open the door, and put your pizza in at a really, really hot temperature. It's wicked awesome. And the reason for this is that stuff like pizza, if you actually go down to your local pizza joint that makes really good flat crust pizza, they're doing it on a fire that's like 800 to like 1,000 degrees. I actually went down to the pizza joint in Cambridge where I live and like took that little IR thermometer. That's what it looks like. Best cake toy ever, as I said. And metered it, and theirs was like 1,000 degrees. You can cook a pizza in about 45 seconds. And it comes out fucking delicious. But you might break your oven. So on the left is the surviving pane from my oven. On the right is a piece of pyroceram 3. It's what the US military used in the 1950s on nose cones of missiles. It's heat rated and stable to like, I think, 1,500 degrees Fahrenheit. So basically, I cracked my oven through thermal shock. Like a little drop of pizza sauce like fell, hit the glass, and it went Yum. So yeah, people like to talk about dry ice, liquid nitrogen actually, and ice cream. What I don't get is why no one's thought to take a bottle of like Goldschlager into the mixture. Because ethanol doesn't freeze until a really cold temperature. Liquid nitrogen's colder. So you can make like ice cream that's like an entire shot in a scoop and like get hangovers from ice cream, and it's really, really good. I was gonna do a demo for you guys today, but I didn't have a liquor license for New York. So there's this thing called an anti-griddle. It's basically a plate that's really cold. You can think of it like a griddle, but instead of making things hot, it makes things cold. They're really expensive. I couldn't get my hands on one, so I made my own. Dry ice with ethanol with a 6-inch square plate of steel from McMaster-Carr. Basically gives you a cold service, and my handy dandy IR thermometer tells me like cold. You can do things like spray like mousses and stuff on it, and like get this thing that's like a pancake where the middle's like warm and like good, and the outside's like hard and set, and like pick it up like a little sandwich and like eat it. If you look at a lot of modernist cuisine stuff like Alinea or El Bulli over in Spain, like they use this stuff to do unusual things from a temperature point of view. But it's really cool. You can play with it. Speaking of El Bulli and Alinea and Fat Duck and places like that, who here has heard the term molecular gastronomy? Who here likes the term molecular gastronomy? So in the culinary world, it's pretty much despised as a term, which is kind of, it's been an interesting thing to learn more about. Hervé Tisse, who's kind of responsible for coining the term, himself says that molecular gastronomy is what you do in the lab. It's the study of physical and chemical changes in food, and that what you might do in the kitchen would be maybe molecular cooking. I've heard somebody else say modernist cuisine, but playing around with stuff in the kitchen, it's kind of like fashion on the Paris runway. 98% of it kind of is bad, and 2% of it's really awesome. So it gets this kind of bad rap sometimes of doing unusual things in the kitchen, because a lot of times you see the knockoffs where it doesn't really work. But when you see something where it really is magical, it's amazing. So a lot of modernist cuisine stuff, for lack of a better term, relies on food additives. These 3 things all have food additives in them. Here's a nice little handy dandy table. I'm going to skip, it's in the book. This is a little video of me taking one of these gelling agents and actually like just playing with it. So that's water, 98% water and 2% carrageen. You can do stuff instead of water. You can do stuff like this. Is what? We know where your mind is. So this is 98% rum. Unfortunately, it tastes like 98% rum, too. But if you cut it with orange juice, like 40%, 50% orange juice and 40 or 50% alcohol, you can make really nice Jell-O shots that are like unlike anything you've ever had. You can also nail them to a wall. When working with this stuff, basically boil it. This particular stuff right here is agar, and I've got these nice little vials of agar for you guys to take home. Did everyone get a handout? Who did not get a handout yet? You guys did not get a handout? Okay, who has the pile of handouts? Keep your hands up, let them see. On your way out, you can pick one of these up. I'll be up here with a table of them. This is 2 grams. There's a recipe on that handout to make chocolate panna cotta using agar. Chocolate panna cotta. Basically, you throw it in liquid, you boil it, and it gets thick. That's just a 1% solution. There's different types. Some gelling agents produce this really firm, like thick thing, which is just balanced in the spoon. And other types kind of give you this flexible gel. But they retain their memory of their shape. They're true gels. That's what the chocolate panna cotta, just a really quick photo, looks like. There's other fun things in the modernist cuisine world. This one's a piece of steak cooked and a piece of chicken cooked that have been bounded together with transglutaminase. It's basically meat glue. It takes 2 different proteins and literally like cross-links them, and actually from a molecular level does covalent bonding on them. So yeah, it's actually a little scary to work with because, we're made of protein. Oh yeah, okay, I kind of said this as we went. Things that surprised me. Hey, what do you know? So we probably just have time for a few questions. Go for it. Favorite source for buying things? The internet. It depends. Kind come see me afterward. I've got a list of, there's actually one of the pages in the book's got a list of places. Next question? Black shirt. Where do I get my liquid nitrogen from? Iggo's Welding Supply. Red shirt.
When you take cream and you churn it to make butter,
Mm-hmm.
you just by shaking it a little bit. What's the chemical reaction that's actually taking place?
Why does cream turn into butter? I can give you an educated guess. I'm not sure. Fat globules in the milk, you're actually shearing parts of them off, and then they can stick to each other, and so you get a metastructure that can actually, the globules kind of form this big long chain, the kind of three-dimensional mesh.
When does the book come out, or has it come out?
When does the book come out? I love you. So I have galley copies you can peek at. I can't give them to you. My publisher, who is O'Reilly, would kill me. It's due out August 3rd. You can pre-order on Amazon. You can go to cookingforgeeks.com and hit the big buy a copy button, and I'll love you even more. Here, take a look. Green shirt.
What's a good source of information, particularly food science, particularly about vegetables?
Good source for food science about vegetables. I have not found good sources for vegetables. As I was saying earlier, it's one of these things that the food science world has not studied as much. I mean, you can get into the journals. I mean, go look at Food Science Journal. I mean, there's for vegetarians. Broaden. Yeah, I realized, based on the gentleman's comment earlier, that I have talked a lot about meat, which really sucks for you vegetarians. But I swear, there's a lot more of interesting stuff in the book. Like, it's not like meat heavy. Good source. I will have to think about that. Send me an email and I will dig up more. Red shirt?
There's actually a book which I have read most of called On Food and Cooking.
Yes, Harold McGee's book on food and cooking.
Yeah, and it actually has a lengthy discussion about like cooking stuff and how acidity affects cooking with broccoli and such.
Yeah. pH is really important, actually. So a lot of the temperature things that I mentioned earlier differ by pH. Like pH will affect it. Things like Maillard reactions, pH will definitely affect the temperature that they happen at. You can actually get down to room temperature. Self-tanning, instant tanning stuff is a Maillard reaction. Black shirt?
You mentioned briefly about genetics when it comes to food tasting ability. What about food preference? We notice my son, for example, doesn't like much sugar, does like
Okay.
bitter things, and
Oh, no problem. I'm sorry, but I'm being told that we have to wrap up because we're out of time. Come see me afterward. I will be out around the corner. Please come pick up one of these if you want. Thanks.
No, it's okay. No worries. Earlier, we don't have one right now in this room. No. I'm not sure who the next speaker is, but they'll need to.